Whew, that's a little bit too much, isn't it? All right. So going over problem number 1, as I walked around, you guys did a nice job with the properties of exponents. Most of you took some time to rearrange the problem to start with, which is a nice technique. I put my integers together, and I put my variable parts together using the associative property of multiplication there. So I have 4 times 3, pretty simple there, it cooks down to 12. And then you have x to the 1/3 times x to the 3/4. We learned last week that when you have like bases multiplied together, you are allowed to add your exponents. So I then had to add 1/3 and 3/4, but you need a common denominator. The common denominator for 3 and 4 is 12. So essentially what I had to do there was add 4/12 to 9/12. You do get 13/12 for your exponent for x. But then I had to look at the directions. I'm like, oh, I got to leave the answer as a radical. Well, the 12 doesn't have a rational exponent to it. So the 12 gets to stay put. And then I have to take the 12th root of x to the 13th power and simplify. What's up? Oh, that's awesome. Good job, Tammy. So yeah, you ask yourself, how many times is 12 going to 13? It's 1 time. So 1x comes out and 1's left over underneath the radical. Ka-ching. Okay. Questions about the first one? Because if you didn't understand the first one, the second one probably didn't go very well. Okay. The second one was a little bit different because you had to apply sort of, I call it that distributive property for exponents, even though it is not really a distributive property. So that's what I did. I pushed in the exponent for 1/2. So I got 2 to the 1/2, x to the 1/2. And then I pushed in the exponent for 1/4 there. So I have 3 to the 1/4, x to the 1/4. And then I did my rearranging. So very similar to the problem before, I put 2 to the 1/2 and 3 to the 1/4 together. And then I put x to the 1/2 and x to the 1/4 together. Excuse me. So 1/2 and 1/4, add those together. That's going to give you your 3/4. Whoop, that's too much. You'll see I got a common denominator there to make that happen. So when I went to go add 1/2 and 1/4, that's the same as adding 2/4 and 1/4. So you'll see I'll get 3/4 in the next line down. It's a little bit tricky about this one right now is the rational exponents attached to my integers. I have 1/2 and I have 1/4. If you think back to last week, when you raise something to the 1/2 power, it's the same as square rooting it. When you raise something to the 1/4 power, that's the same as taking the 4th root. We don't have a product property that allows us to combine those two radicands. Product property only applies if your indices are the same. So our workaround on that is to play around with the exponents a little bit. So this is a pretty cool trick. Do you see I circled the 1/2? I turned it into 2/4. Everybody follows that 1/2 is the same as 2/4. Okay, then what's kind of cool is I see that they both right now have denominators of 4. So I could actually pull out, I'm actually using that power property in reverse. I'm going to pull out the 1/4 outside of a set of parentheses. It's like I'm doing that distributive property for exponents, but in reverse. Do you see that? So I pulled the 1/4 out, and then I'm like, oh, easy. I got 2 squared and 3 to the 1st. I can do that math. 2 squared is 4 times 3, that's 12. So it's like I have 12 to the 1/4 power. Oh yeah, and then x is also raised to the 3/4 power. So now it's easy to write it as a radical. Isn't that cool? Cool trick. A little magic. I like it. It's just a different way of thinking about the power property. Kind of cool. Gives you a little flexibility in your thinking. So my next step down, because hey, this person said, hey, I want my answer as a radical. I had to rewrite 12 to the 1/4 as the 4th root of 12. And x to the 3/4 is the 4th root of x cubed. Now, because my indices are the same, power product away. I said that wrong. Product property away. Multiply 12 times x to the 3rd. You get 12x to the third, all underneath your fourth root. Blah, blah. Couldn't talk there for a second. Okay, questions about that one? A little weird, but kind of cool. All right, so today's mission, we're solving for x. That is what we are about to do. So you have basically 4 steps that we're going to jot down in our notes. So on my next slide here, I lied. A couple more slides. We get our 4 steps for solving for x. I'm going to go ahead and give you a minute to fix that. Steps here. In general, there's 4 steps to solving for x in a radical equation. I summarize them: isolate, eliminate, solve, and check. And you're probably saying, Mrs. Lucas, you always tell us to check. Do I really have to check? Well, in this section, in this particular chapter, it's super important. Sometimes our algebra solutions or our algebra work produces solutions for the problem that don't actually exist. And those solutions are what we define as extraneous solutions. So I have one more vocabulary term to add in for today. Extraneous solutions, if you look at the root word there, it's like extra. And that's really our definition. They're extra solutions. Extra solutions that do not work when substituted back into the original, emphasis on that word, the original equation. Extraneous solutions are defined as extra solutions that do not work when you plug them back into the original equation. You must always check your work. So we're going to run through our 4 steps. We isolate, we eliminate, we solve, we check. In problem number 1, I'm asked to isolate that radical. Isolate, if you feel isolated, you feel alone. To isolate something means to get it by itself. And if I look at that radical expression right now, the square root of x plus 5 with x plus 5 is my entire radicand, that radical is by itself. It's already isolated. So step 1, you'll see sometimes there's like an if possible or if needed next to it. In this case, it wasn't needed. So I can move on to the next. After I isolate the radical, I can get rid of it. Remember, my goal here is to solve for x or get x by itself. So eliminating that radical makes the problem a lot easier to work with. Notice if it's a square root, you could just square both sides, the whole sides of the equal sign. So a square root gets rid of a square. Much like in the last chapter, we used a square root to undo a square. They're inverses of each other. So I can do that. So x plus 5 is left over on the left. And then on the right side, I have 12 squared. It's 144. In step 3, I have to solve for x. This usually requires us to go, backwards through our order of operations again. I would just subtract 5 from both sides. Let me show you that. So here's me balancing my equation, subtracting 5 from both sides. So you get x equals 139. I'm going to go ahead and check this. So when I check it, I'm going to take 139 and plug it back in for x in the original equation. 139 plus 5 is 144. The principal square root of 144 is definitely 12. So that answer works. To be completely honest with you, in all transparency, if I would have changed one symbol in the problem, this answer for x would not have worked. If I would have, just for fun, you don't have to write this down, if I would have made this 12 negative, 139 still would have been the answer I got for x, but it wouldn't have worked. Anybody tell me why? Do you know, Tammy? Yeah, very good. When I take the principal square root of something, I'm looking for that positive value, and she said it. Positive 12 doesn't equal negative 12. So make sure you're checking your work is the moral of the story there. You want to check to make sure that your answer is indeed non-extraneous. So you'll get an answer and do all the work right, but it still might actually not work in the original equation. Okay, lather, rinse, repeat for number 2, right? So we have 4 steps. We isolate, we eliminate, we solve, we check. So I'm going to isolate this radical right here. I have the cube root of 6 plus x. It's already isolated. There's nothing, there's no coefficients out here in front. There's no numbers tacked on to the end. Step 1 is done for this problem. Step 2, I want to eliminate a cube root, which just means I'm cubing both sides. And little help. I don't have my calculator out. I need to take 12 to the 3rd power. 1,728. Thank you very much. So I eliminated the radical, and now it's kind of easy to get that x by itself. I would just subtract 6 from both sides. And we get 1722. You could also check these in your calculator. I just wanted to show you where those buttons are real quick. So you would just go ahead and, if you want to take the cube root of something, just a little reminder there, it's in your math menu, and it's the 4th option down. And we're checking right now 1722 plus 6. Oh, look at that. 12 is my answer. So it worked out. Pretty cool. Questions about that? Okay. So again, in the next example there, I'm looking at number 3. Just a little disclaimer, if you're a person who writes large for this problem and the next one, you probably want to write small. How's that? Good. Are there any questions on the first couple? Because I didn't have to isolate the radical at all on those, did you notice? On number 3, though, do you see how that radical is not by itself? Oh, man. There's an x, a minus x, specifically keeping it company. So this is where step 1 comes into play. The radical is not isolated because there's something else along with it on the same side of the equal sign. So to isolate the radical, you got to get rid of that stuff. Do you know what you do, John? Oh, I thought I saw your hand for a second. Yeah, you'd have to add the x to both sides. Keep in mind, I like to write my polynomials in standard form. So on the left side right there, what do I have left over? Just the square root of 2x plus 7. And then on the right side, I have x plus 2. So step 1 is done. The radical has been isolated. After we isolate, we eliminate. So I need to get rid of that square root symbol there. I'm going to square both whole sides of the equal sign. What you do to one side, you have to do to the other. The whole other side. Do you see how I put it in parentheses and then squared it? Super important. All right, so what's left over on the left side is 2x plus 7. And on the right side, I actually have x plus 2 times x plus 2. I'm going to need to call on my understanding from our previous chapter when we solved quadratics in order to solve this equation. So I would FOIL on the right. FOIL stands for first, outers, inners, last. So I have x squared plus 2x is plus 4x plus 4. And then I'm going to get one side equal to 0 because I really can't solve a quadratic with factoring unless I do that. And that's usually my choice method because it's the fastest. So I have 0 on one side. And on the right side, I have x squared plus 2x minus 3. And then I got to think to myself, what are factors of negative 3 that make 2? Factors of negative 3 that make positive 2 are just positive 3 and negative 1. And now I have two things multiplied together to equal 0. That reminds me I have to use my 0 product property. So I'm going to take x plus 3 and set that equal to 0. And x minus 1, I'll set that equal to 0. And then I solve. I'll go ahead and let you know that one of these answers is garbage. One of them does not work. So I have to check. They may have any questions about step 3. I solved that for x by getting one side equal to 0 and factoring. They may have any questions about step 3 before I check step 4. We're good? You guys were pretty good with this stuff. I'm not surprised. Okay, so now what we're going to go ahead and do is check our answers by plugging them into the original equation. So I'm going to check negative 3. Negative 3 times 2 is negative 6. Plus 7 is 1. The square root of 1, that's just 1. So this evaluates to 1. Minus a negative 3, because that's the value of x we're checking, that's 4. 4 does not equal 2. So the x value of negative 3 is garbage. It's an extraneous solution that the algebra forced out that doesn't work when you plug it back into the original. Now I'm going to check 1. If I check 1, 2 times 1 is 2, plus 7 is 9. The square root of 9 is 3, and then 3 minus 1, hey, that's 2. It totally works out. So this guy works. Just something to keep in mind. Trying to think if I want to show you on your calculator. I'll just draw a picture. I don't need the calculator to do this. If you think about it, the square root of 2x plus 7, take away a value of a constant, you're kind of looking at, maybe a half a sideways parabola there, running into a horizontal line at 2. Really, that's only going to happen one time. Ooh, what's up? Well, I think so. Yeah. I think so. So far. I haven't finished making it. True confession. So I think, so far, yeah. Are there questions about this so far? All right, number 4. This will be our last problem of the day. And then independent practice, that part 1 will be our warm-up for tomorrow. We isolate, step 1. It's already isolated. Step 2, we eliminate the radical. So in this case, it was a cube. I'm going to cube both sides. So if I cube the cube root of 25x, that's just 25x. If I cube the right side, I get 125x to the third. And again, I really can't solve a polynomial unless I get one side equal to 0 here. At least we can't in this particular class. And then I'm going to lean on my mad factoring skills. I see there's a GCF of 25x. Wow. To be continued for tomorrow. Yeah, you do.